Hi, this is Abhilash Majumdar. I'm a research scientist working in Morgan Stanley. Previously, I have been working in NLP engineering in HSBC Holdings. So I have been maintaining Google research repositories like BERT and Albert, and have also been training students and professionals in different aspects of AI, NLP for organizations like Udacity, Udemy, and Upgrad. So I have exposure in this field in mentoring everyone. So also welcome to Co-Learning Lounge YouTube channel. So as you know by now, we have lots of videos on different aspects of NLP. And going forward, we will be having more videos on different aspects of transformer models like GPT, GPT-1, GPT-2, and robust architectures. So you can connect with me in the links provided in the description. Also, feel free to comment on the previous videos and on this video as well for feedback, and be sure to subscribe to this channel for future videos. So moving forward, in today's concept, we are going to understand about BERT. So previously, in the last video, we talked about attention mechanisms. We saw how self-attention plays a significant role and how transformer architecture is built by using query key and values pairs. And we have seen how self-attention, when they are taken 8 at a time, that resembles a multi-head self-attention. We have essentially created the first or the classic transformer model that resembles, having 8 encoder decoder architectures, each having self-attention modules inside of it. And this beautiful architecture of a transformer is what paved the way for future advancements. And we come to the classical aspect of BERT. So BERT is a very classical example of a transformer architecture which has provided a benchmark that is revolutionary in the context of NLP. So Google's BERT has transformed the natural language aspect, especially all the natural NLP landscape. So in this case, we are going to talk about BERT. What is BERT? How BERT is built? What are the different aspects of BERT? How the transformer is architecture is inside BERT. So this is not, we are generally in the case of having a transformer model, we apply different language modeling tasks. So it can be machine translation, which was the example taken in the previous videos. We also had features like text classification and all other variants of language modeling tasks like summarization, question answering. So BERT is a multi-purpose NLP model or language model which can cater to different aspects of NLP. So Google Research BERT is one of the most, I would say, beautiful and state-of-the-art language models up to date. And there have been lots of variants of it. And it is not an exaggeration to say that BERT has significantly altered the landscape of NLP. And because this is trained on a large unlabeled data set with the transformer model that we previously saw, and lots of modifications on top of it that we will go into. But classically, it's a classic transformer model, which is trained on a huge corpus. And there are so many intermediate hidden layers and hidden interactions, computations being done inside BERT, that different layers, when we abstract the information from different layers, we can fine tune BERT for different language modeling tasks. So in this case, we are going to talk about BERT. So BERT essentially stands for bidirectional encoder representations from transformers. So that is where the abbreviation BERT comes from. So bidirectional encoder representations. So from this term, we can guess that we know already that what an encoder is. Bidirectionality comes from the fact that we are using bidirectional stacks of RNN variants like LSTM, GRU inside of it. And transformer means that we will have essentially self-attention mechanism, scale dot product attentions with multiple heads combined together. And this is what the BERT is. So it is designed to pre-train deep bidirectional representations from unlabeled texts. So unlabeled texts generally refer to an unsupervised kind of a learning. And this is done by jointly conditioning on both sides of a particular context. So when you are applying BERT on a particular sentence, on a corpus, so taking one word or a phrase of words as a pivot on both the left and the right side of the context are taken into the picture. And BERT, there are many variants of it. And this is where the pre-training of BERT and the fine-tuning of BERT comes into the picture. Because just like I mentioned, the additional output layers and the individual hidden layers of BERT can be abstracted for different language modeling tasks. Now, this sounds, little bit more complex. So if we were to summarize, what are the most important aspects of BERT? The most important aspects are BERT is, a standard transformer where you have bidirectional representations. It tries to capture both information forward and backward in a look ahead and a look back manner. It tries to pick up as much context as possible, as we know by multi-head attention rule, right? And it can be considered that BERT is the base transformer architecture. So all the transformer architectures that we see nowadays, like large scale BERT, Distilled Bird, Roberta, Albert, and all these variants that we'll be seeing a little late, all these kinds of things are derived from this BERT model. The pre-training, the pre-training part is just the half of what BERT's success is. Because when we try to train a language model on a large text corpus, so it can be unlabeled corpus, right? So the model starts to pick up, intermediate or hidden contexts. And these contexts are in latent dimensions. That means these are in latent spaces. And when we want to know about different contexts which are arising from a particular corpus or a particular paragraph, we are applying multiple times that self-attention rule, and this actually improves the performance of BERT. So if you were to try to find out the context of this particular example that we see, we went to the river bank and I need to go to the bank to make a deposit. So in this case, the word bank has two separate contexts. And when we try to use these two sentences in conjunction, the language model should be able to predict what is the sentiment or what is the context when the bank is used in the first sentence, which is in the case of a river, and when it is used in the second context, that is when it is used in the terms of financial organization. So we have already covered lots of ground on different NLP tasks like word2vec. We have covered about Elmo, right? We have already seen what static pre-trained embeddings kind of they do. They try to apply these kinds of embeddings on a higher dimensional plane, and they try to fit some cosine similarity on top of it. BERT is a little bit different. We have already seen the architecture of a traditional encoder decoder, which generally fits an Elmo, right? So all of this have previously been covered. So now, when we move forward to BERT, so the BERT consists of a beautiful architecture. So there are two variants. When Google Research released the BERT model, there were originally two variants, the BERT base and the BERT large. So BERT base has 12 layers of transformer blocks, 12 attention heads, and 110 million parameters. So that is quite a large number of parameters to be trained for a neural language model. And BERT large is even larger. So it is 24 layers of transformer blocks, 16 attention heads, and 340 million parameters. So it is much larger than what BERT base is. So the BERT architecture can be considered like this. So you have a stacks of encoder cells, which are 12 in number, and correspondingly, you will have a corresponding stack of decoder cells, which are again 12 in number. And why these are called transformer blocks? Because as we recollect from our previous video, we have inside the encoder block, we have self-attention, right? And we have feed-forward neural networks inside of it. So inside a particular encoder layer, we already have self-attention and feed-forward neural network. There were intermediate layers like add and normalize and all these kinds of layers. But essentially, these two fundamental parts were there in a particular encoder cell that we see. And these resemble, when we try to combine these different encoder cells or stack them on top of each other, which is 12 in number in the case of BERT. So that essentially becomes our transformer architecture, right? Transformer block. Correspondingly, the same is there for the decoder as well. So the decoder essentially contains the attention, the self-attention block. It contains encoder decoder attention as well as the feed forward dense neural network, right? So all these kinds of things are already we have studied in the previous videos. So encoder and decoder blocks are essentially the architecture which is there inside BERT as well. Just the number of decoders and encoders changes in BERT base and BERT large. And this effectively changes the entire landscape of how BERT preprocesses, how BERT fine-tunes, and how BERT pre-trains for different language modeling tasks, right? So the next thing is text preprocessing. In the case of BERT, there are three different aspects. So one is called as the position embeddings, one is called as the segment embeddings, and one is called the token embeddings. So as it is given in the figure over here, the token embeddings are essentially derived from specific tokens. In the case of BERT, there are two special tokens. That is, one is called as CLS and the other is called as SCP. The CLS denotes the starting of a particular phrase or a particular sentence. The SAP denotes the end or the terminal position of a particular sentence. So these tokens are essentially important when we want to have a corpus like question answering, when we want to have a corpus like multi-level classification, or when we want to have multiple choice questions or multiple choice question answering system. So in this case, it is very much important to have these kinds of tokens, that is the CLS and the SCP, that denotes the start and the ending position of a particular question and the start and the ending of a particular answer related to that particular question. And this is where the concept of token embeddings comes into the picture. This is just like adding CLS and SCP to a particular text corpus that you have. Now, the next part is the segment embeddings. This is a very important part because it takes sentence pairs as input generally for tasks like question answering, right? And that is why it learns a very unique embedding. It creates a very unique embedding for the first and the second sentences to help the model distinguish between them. Like, you are having different kinds of segments created. What the BERT internally does, it tries to create an embedding matrix essentially, and it takes the first and the second sentences to help model and distinguish between them. So internally, you can think of them this like a classification model which is happening inside of it in the segmentation embeddings. With the help of these embeddings, when they're passed to the encoder and the decoder architectures inside BERT, automatic segregation and context wise or context level separation comes into the picture. And this is very, very important. And this is where the segment embedding comes into the picture. Now, as a rule of thumb, or you can say in a simplistic manner, when you are having a question answering pair, you are generating a segment for the questions. So let's say we have a question like, when was the Taj Mahal built? So this is a question. Now this question will have segment A because it represents a question pattern, and it will have a corresponding context from where the answer can be derived. This particular context is known as the segment B. So generally in question answering pattern, this is clearly observable. Even in the case of, if you want to fine tune BERT for classification tasks as well, then also the segment embeddings can be used. Then we have the position embeddings. Now we have learned about position embeddings in the transformer case, where we mentioned that these are vectors, position, embeddings created from the position vectors of a particular word or a particular phrase of words in a sentence or in a question or in an answer or in a context. So essentially, BERT learns and uses positional embeddings to express the position of the words in a sentence. And this is very, very important because as we recollect that attention is all you need is a very famous paper in the context of NLP. And it was hypothesized by the Google research team that to have a sinusoidal kind of a positional embeddings feature when we are applying attention. And even if we go into the research paper, it is clearly mentioned that they took sine I pi by 200 as the essential metric for creating this kind of positional embeddings. And this adds effectively to the embedding matrix that we're generating. So positional embeddings, token embeddings, and segment embeddings are nothing but more added inputs, more added parameters, which get added with the original input vectors or original embedding matrix. So this essentially creates a very robust and a very highly efficient language modeling input that can be fine-tuned with the help of the encoder decoder architecture. The next phase is applying that encoder decoder architecture or the transformer architecture inside BERT. So essentially, this is what it does. So position embeddings are nothing but applying position vectors to each and individual words in a sentence, or it can be phrases of words as well. So these are added to overcome the limitation of the transformer. So in a classical transformer, we did not get these terms. In a classical transformer, we only had stacks of encoder decoder cells with self-attention, multi-head self-attention like that. But in the case of BERT, we have added this modification that position embeddings are there. We have segment embeddings and we have token embeddings. So for a given token, the input representation is constructed by summing the corresponding token and the segment and the position embeddings. So instead of having just the input embeddings, we are having the token embedding, we are having the segment embedding, and we are having the position embedding. So we are adding all of them together. These combinations make BERT very versatile, right? And there are many pre-training tasks that we can perform on BERT. So two of the most famous tasks that BERT works on is known as next sentence prediction, that is NSP, and masked language modeling. So there are different aspects of causal masked language modeling, but in the general masked language modeling, this generally refers to as predicting a given word when you are surrounding it with a particular context. So you're masking certain parts of the corpus, and you want to predict that particular masked word or a masked token. Essentially, this is referred to as a token. So as it is rightly mentioned over here, The network effectively captures information from both the left and the right, because BERT is a bidirectional, a bidirectional transformer. So it effectively applies bidirectional variants of LSTMs or recurrent units inside its encoder models, and then it applies this, self-attention mechanism. So essentially, it takes the context from both the left and the right part of a particular token, or essentially a word, right? And then it tries to build, a meaning out from it, derive a context vector out from it. And what this helps is, because when you're trying to, let's say, mask that word or remove that word in a particular, in the same sentence, and we want the BERT model to predict what is that particular word that we have masked, then this bidirectionality, the weights that get, preserved, if it after we train the BERT model, that helps us to predict correctly the masked word. And this is generally what BERT is. Actually, the masked language modeling is very, very important. And throughout the use of BERT and all other different transformers, this is by far the most applicable context of applying a transformer. And the use of BERT model is not only restricted to MLM, but also question answering and text summarization and all these kinds of things. So if you see the example over here, Google search, right? What is the, we apply a question, what is the, and we can see lots of suggestions, right? And these kinds of suggestions are nothing but MLMs, right? Masked language modeling, where we are trying to predict, phrases of words, right? We are trying to mask certain phrases of words, and we are trying to predict what the BERT model outputs as collection of words, right? So there is a deep, bidirectional model that is more powerful than either a left to right or a shallow concatenation of left to right and a right to left model. So bidirectionality essentially powers your model to create context vectors from both the left and the right, instead of, either in a forward pass or in a backward pass. So when we are comparing the different attributes, or when we are comparing the different features of, let's say, Elmo and BERT, so in this case, Elmo, we can see that this is our traditional architecture that we have previously saw, right? These are stacks of bidirectional LSTM cells, and for each and every LSTM output, we are passing it to the corresponding decoder cell. But in the case of BERT, this is very, very different. And we can see that for individual, for each individual hidden output of a particular encoded stack, so it is concatenated to each and every one of the encoded stack or decoder stack to the next level of the next level. So you can see that there is a higher, interlinking of the intermediate outputs for each of the intermediate stacks of the BERT model, instead of just having a 1:1 modeling, right? So mapping. So in this way, this BERT model achieves a very good efficiency about different modeling tasks. And this is what the masked language modeling is. In generally, if you are applying masked language modeling using BERT or any other BERT variants, we generally refer a token called as mask, which is denoted over here, right? And this is the token that represents the missing word that we're going to find. So if, like in this case, we have seen that I love to read data science blogs on masks. So this mask essentially helps to, allows the BERT to recognize this token as something that needs to be predicted by the model, and the BERT essentially predicts that. So and there are certain modifications of it as well, to prevent the model from focusing too much on a particular position or a particular token that are masked. The researchers randomly masked 15% of the words, right? The masked words were not always, replaced by the masked token, because the masked token would never appear during the fine tuning task. So the researchers did the following technique. They have applied 80% of the time, they have, the words that were replaced with the term token, the particular token mask. 10% of the time, the words were replaced with random words, and the rest 10% of the time will left remain unchanged. The second part where BERT comes into the picture is known as NSP, or next sentence prediction. Next sentence prediction is a very classical feature for any language model, and we have seen it from word2vec as well. So BERT is also trained on the task of NSP for tasks that require an understanding of the relationship between the sentences. So in this case, there have been various adaptations like MLM, but more or less, these are some of the important features. So NSP is just an extended version of it. And the people of Google research, they have taken up different examples for this purposes as well. So in this case, we have mostly covered what BERT is in a nutshell. But if we were to move into the internal architecture of what BERT is, we will be referring to this blog by Jay Alamar. And this blog is essentially a guide for BERT. But since we are going to use a variant of BERT, which is known as Distilled Bird, a lighter version of BERT, which is trained by Hugging Face, one of the most popular repositories and one of the most popular organizations in the field of NLP. So in this case, we are going to see what Distilled Bird is, right? Because Distilled Bird is just a smaller version of a particular BERT model, of the traditional BERT model, and it generally is a lighter version, and it gives faster efficiency without dropping much performance. Okay, so in the case of context, sentiment classification context that we see, we have a particular IMDb classification task where these are the movie reviews of the IMDb corpus, and these are the corresponding labels. So our task for the BERT model is to train, or for the Distilled BERT model is to fine tune this task for classification context. So sentence sentiment classification is a very important task for BERT models. So we are going to talk about Distilled Bird, as I mentioned, and Distilled Bird is a lighter version of a BERT, and most of the concept of Distilled Bird is taken from the BERT itself. So if you are considering the architecture of Distilled Bird, in traditional BERT, the vector size is always 768 in traditional BERT model. That is the BERT base model. Now, we can think of this vector as an embedding for the sentence that we can use for classification. So as I mentioned, there are three different embeddings that are getting created in the BERT model. That is, the position embeddings, we have the segment embeddings, and also the token embeddings. We will keep them as it is. Just an additional point, the vector size of the BERT models is just restricted to 768. So this vector we can create as an embedding, as an additional embedding layer. So once we create that embedding layer, the next part is very simple. It's like applying any traditional classifier, or it can be it can be anything from scikit-learn, or it can be anything, any neural network classifier for our use case. So in this case, when we are talking about Distilled Bird generally, so Distilled Bird essentially tries to create first a sentence embeddings for all of the different sentences. So you can create word embeddings as well, and you can also create sentence embeddings. And since the BERT model, original BERT model, as well as the Distilled Bird model are trained on very large corpuses, unlabeled corpuses, so these embeddings are always generated. Like these can be thought of similar as Elmo embeddings, but the dimensionalities are changed, and these are more robust as compared to Elmo. So we do not consider or touch Distilled Bird after this step. So the next important aspect is the particular size attributes of what the internal layers in a particular Distilled Bird model is. So if we move below, we can generally see that the first step in a particular Distilled Bird model is that, or in a BERT model, is to tokenize the data. And as I mentioned, in this case, the tokenized embeddings are getting created. We apply the CLS and the SAP tokens at the start and the stop and the end of the sentence, respectively. Once we have done tokenizing the data, the next part is the flowing through BERT model. And in this case, we apply the segment embeddings and we apply the positional embeddings as well. And when we apply the segment and the positional embeddings, we then pass it through the stacks of encoder and decoder architectures. So in the 12 stacks of encoder BERT base, that is 12 stacks of encoders and 12 stacks of decoders, right? Inside of it, we have that robust architecture of self-attention mechanism multiple times, that is multi-head attention. That remains particularly the same. And if we move forward, the rest part of it, that is the output of the decoder model, is passed through a feed-forward network, as in the case of a traditional transformer. And we can pass it through, the output of that, we can pass it through any neural network classifier or traditional classifier. So if we move to the architecture, there are certain important features of BERT. So when we are doing any fine tuning or particular task like question answering or generating embeddings, only abstracting the embeddings from the BERT model, right? Pre-trained embeddings from the BERT model. What we do, we only abstract the last output or the last hidden cell from the hidden layer of a particular BERT model. And this is very, very important because, and this is mentioned over here. So if you want to unpack the BERT output tensor, an output tensor is generally derived from the output of the decoder. That means once we have the tokenized input with the CLS and the SAP, we generally pass it to the, we generally add the sentence embedding, segment embeddings, and generally create the, the positional embeddings, and then we pass it through the stacks of encoder and decoder architectures. And when we have finally pre-trained it, which is obviously done by the Google research team, we can then actually fine tune it by abstracting the last or the hidden, last hidden states. And this is denoted by the last hidden states 0. That is the first tensor, right? So this is the pictorial representation of that particular output that we're going to see. So BERT output tensors or predictions are denoted in the terms of 768 hidden units, because in a BERT vector there are 768 hidden units, right? So number of the number of output rows that we have, that depends upon the model input sequence and also the input embedding matrices. This is dependent on the input features that we give, but essentially whatever output we generate, it is going to be question mark comma 768. The question mark is the input features that we want to allocate to BERT, or send as input to the BERT. The 768 is the fixed length vector size that we get as output. The last hidden states are to be extracted when we want to extract the BERT embeddings for any fine tuning tasks. So when we want to create this or elucidate this journey, so what we generally do, this is summarized in this beautiful pictorial representation here. So we first tokenize the sentence, we apply additional segment and positional embeddings, right? And then we have the input IDs corresponding to the tokens, and then we pass it in batches. In most of the cases it is done in batches to the BERT model, which is nothing but a transformer model comprising of 12 stacks of encoder decoder cells, and inside each encoder decoder stack we have that self attention mechanism working operating inside of it. So, and there are corresponding add and normalize and feed forward neural networks inside of it. And when all of this is done, we can abstract the last hidden states or the last hidden output of that hidden here of that particular BERT model, pre-trained BERT model, and we can get our tensors, output tensors or output vectors for a particular classification task, or it can be any other task. It can be question answering task, or text summarization, or any other tasks. So as I mentioned, there are another nitty-gritties to this important aspect. So when we want to extract the last hidden states, we have to extract, if we are using Python, and most of the cases we are using Python, only we have to extract the first position, that is the CLS, because genuinely the CLS denotes the starting of a particular answer or a particular token, right? The CLS token is the start of a particular answer. It can be a particular answer to a question. It can be a particular sentiment covering a particular text classification context. So whatever comes after the CLS, whatever tokens or whatever numerals or the integers that come after the CLS token in the output, that should be collected. And this is given over here. Only the first output position, that is the CLS, and whatever all the hidden output cells, whatever comes after that should be collected. And the first dot denotes all the sentences. That means we are covering all the sentences. We are extracting the context from all the sentences that we see. And we are taking, we are considering ourselves from only the CLS token, that is the start token. This is denoted as the start token, which is denoted in the red sign over here. So whatever comes after this, we are taking into consideration in the output tensor. So now the next part is effectively, this is a 3D tensor that we get, right? Which is denoted over here. This is kind of a 3D tensor. So how to scale this into a 2D tensor? Because in many cases, when we are abstracting BERT embeddings, we want to reduce the dimensions, right? So we have to, create the embeddings in such a manner that we can reduce the 3D tensor to a 2D tensor. So this is very simply done using NumPy by just adding .NumPy, appending it to the last hidden states syntax. So what we are doing, we are abstracting, all the sentences, right? The first dots, the colon signifies all the sentences. The 0 part indicates that we are abstracting from the CLS token, that is the start token. And then we are adding .NumPy. This signifies that we are converting from 3D to 2D tensor, which is denoted in this beautiful picture over here. So all the tokens that we see over here, that is from 0 to 1999, that is 2000 tokens, all are classified in a 3D, from a 3D tensor to a 2D tensor. And this becomes an ideal, characteristic for any classification task or any language modeling task that you see. Once we get the sentence embeddings, or particularly paragraph embeddings or corpus embeddings, right? We can do lots kinds of things with it. We can feed it to an artificial neural network. We can feed it to another stacks of our own built encoder decoder layers, or we can build it to another BERT model. We can add it to other robust architectures. So anything we can do. Once we get the sentence embeddings, all of the thing is very much clear, and this can be fine-tuned to any task that we want. So essentially, these are some of the most important aspects. The rest part of it is mostly, the generic form of machine learning and a generic form of classification for any NLP task. So essentially, if you want to summarize what we have learned, the first thing is that BERT is a bidirectional representation transformer model. So essentially, there are two versions of it. One is the BERT base and one is the BERT large. So BERT base has 12 encoder decoder stacks and 110 million parameters. BERT large, on the other hand, has 24, 24 encoder decoder stacks or 24 transformer blocks, and it has 340 million parameters. And all these kinds of parameters are very, highly trained, pre-trained. And if we want to abstract, embeddings from a particular BERT model, we have to follow a series of steps. The series of steps include, the first step includes token, having token embeddings, creating token embeddings, CLS and SCP, right? And then we are creating the segment embeddings. If you are doing it for question answering tasks, then we can do the position embeddings, which is another important feature in the case of self-attention. And then we pass it through the BERT model, right? Inside the encoder stacks, as in the case of a traditional transformer, we have the self-attention blocks and multi-head self-attention, right? And we get the output from the decoder stack of the particular transformer block of a BERT model, right? And once we get the output, we can get the last hidden cells or the last hidden right of the BERT model to abstract that particular sentence embeddings. And once we get the sentence embeddings in 3 dimensions, right, we have to convert them to a 2D tensor, because in most of the cases when we generally see embedding matrices which we are going to feed it into any architecture, neural architecture, we generally need them to be a 2D tensor. So we convert them by adding dot numpy, appending dot numpy to the last hidden states output, right? So how we are taking the output, the first colon signifies that we are taking all the sentences into consideration. The 0 indicates that the CLS token, that is the start token, we are taking into consideration, and everything after that we are taking into consideration. All the tokens, all the numbers that are coming after the CLS token, we are taking into consideration for our output tensor. And dot numpy signifies that we are essentially trying to convert this 3D tensor to a 2D tensor for our use case. And essentially, once we get the sentence embeddings, we can do any task with it. We can do question answering, text summarization, text classification, and all other things that we can. So that is most of the details that we want to cover about BERT. Now, a quick detail about what the different versions of BERT is. So this is from the Hugging Face Transformers library, one of the most popular repositories on GitHub, and one of the most useful repositories in the NLP industry till now, right? So we can see that there have been so many modifications of BERT and so many advancement of BERT that there are so many versions of it. So BERT, we have originally seen that the BERT large or the BERT base cased, right? We have seen BERT base and BERT large. So we can see that there are 12 transformer blocks or 12 layers essentially, right? We have also seen the 768 hidden cells, that is the vector size, that is 768. In the case of BERT large, that gets extended to 1024 vector size, right? So in the case when we abstract the sentence vectors or sentence embeddings from a BERT large model, it will be something of the sort as question mark, comma 1024. So question mark signifies the hidden embeddings that we are going to set previously. And there are other variants as well: BERT base uncased, BERT large uncased. We also have multilingual models as well, which are trained on multilingual corpuses like Chinese, German, French. And these require lots of attention mechanisms. As you know that attention concept is derived from NMT, neural machine translation, which takes into consideration sequence to sequence models like encoder decoder with attention mechanisms. So needless to say that these kinds of architectures are more robust. BERT is a more robust architecture for multilingual question answering, multilingual classification, multilingual abstraction, summarization, and all these kinds of things, right? So the models remain the same, right? The model parameters remain the same. That means the vector size remains the same. For the BERT base, everything remains at 768. For the BERT large, everything remains as 1024. So the vector size remains like that. And so there are different kinds of BERT, right, in this. And you can go through these pre-trained models. And not only BERT, there have been so many advancements in the transformer architecture that you can see lots of other models from BERT as well. So there have been another modification by Facebook called as Roberta, which is another highly trained version of BERT and a much heavier model than BERT. So it contains, you can see that the Roberta base, it almost has similar number of parameters with respect to the BERT base, right? With the parameters are a bit larger. It contains 125 million parameters as compared to 110 million parameters in case of BERT normal or BERT base. And similarly, in the case of Roberta large, it has 355 million parameters, which is quite large than the standard 340 million parameters for BERT large, right? So Roberta is actually a very fine-tuned, I would say, and a very robustly trained BERT, because the people working for Roberta essentially trained it on very large corpuses, very large attention heads,
and they have gained a significant advantage or a benchmark over BERT. But there is another lighter version which I was mentioning before called as the Distilled Bird, which is a lighter version of BERT, but it almost resembles BERT in most of the sense. And the internal architecture of BERT is nothing but a teacher-student framework, where you have a traditional BERT model, right? And you want to, try to the traditional BERT model tries to teach a smaller BERT model, or generally known as the tiny BERT model, to learn, right, or to apply language modeling. So almost the same architecture with reduced number of parameters. As you can see that the Distilled Bird base has 6 transformer heads or 6 layers. The 768 vector size almost remains the same, and the number of parameters is greatly reduced from 110 to 65. So this tiny BERT model achieves almost the same performance as that of a BERT model, but it is way faster than BERT and it is highly performant. And this is why it is the most popular and productionized model in the case of NLP, where there is memory issues and large text corpuses, processing time, and all these kinds of things. So Distilled Bird is essentially a very good model for any task, right? And then we have different other models like Camembert, Albert. Albert is a very sophisticated other model from Google Research, which is which has not only bidirectional representations, which not only has bidirectional context vectors, but it has 24 repeating layers. That means that the particular transformer architecture that you see, it gets repeated over and over again 2 times generally. For if you're having BERT base, then we are generally have 12 layers or 12 transformer blocks, and in the case of Albert, we have 12 repeating transformer blocks. So in this case, we have the same vector size as 768, and generally this is Albert is we can say that this is a lighter model than BERT, but it is so fine-tuned and so fine and pre-trained on such distinct corpuses that it achieves a very good deal of performance than normal BERT. And we will get we like the Albert model is essentially one of the most popular models to be used till date. And generally, these more details about this model can be found in the Hugging Face repository and in their own blogs as well. Even Google Research has that Albert repository publicly available, and we can generally dive into the code as well. So there are other advancements as well, like applying GANs or adversarial networks for transformers inside the transformers for language modeling tasks. So this is done in the Electra model, which is the latest model, transformer model, by far the latest transformer model from Google Research. There have been other advancements like T5, which is another variant of an encoder decoder architecture model. So lots of architectures are getting developed over and over again, and in the successive years we will be seeing that lots of architectures will be getting more developed. So but the core idea about essentially BERT, right, that remains the same. So it is a very robust transformer containing 2 different variants. When it was first introduced, 12 transformer heads and 24 transformer heads for the BERT base and the BERT large. And that is essentially all that I had to cover for this particular video. So and I will see you guys in the next video tutorial when you are going to cover about more details about the different transformer aspects, and how we'll be seeing how the other transformers beat BERT, and also how they compare in terms of scalability, throughput, and efficiency. So thank you, and I will see you guys in the next video tutorial. Thank you.